to a C0 gate, a Bell state measurement, it involves the same sort of nonlinearity and the same sort of interaction between the qubits, but you can destroy them at the end in the sense that you don't need to, particularly in photons, you don't need to maintain the state of the qubits after the measurement, whereas a C0 gate you clearly do. It needs to be part of a larger algorithm. Anyway, the sort of KLM recipe shows you that if you use larger entangled states of more photons, you can, again using this all linear optical recipe, you can make Bell state measurements with arbitrarily high success probability, arbitrarily close to 1. And I won't go into the detail of that, but that's where the real sort of overhead comes in. It's not just 16 pairs of photons.
Does the same problem not apply to actually creating new Bell states and entangled states in the first place?
Potentially, yes. I mean, so if you had two photons in some separable state, then the best way that you could imagine potentially to entangle them would be to use a C0 gate. However, there are sources of photons where you might directly get entangled states, whether that be from parametric Gaussian conversion or from quantum dot sources of photons and so forth. But yeah, in principle. The other thing that I want to emphasize before I get going is that this sort of KLM recipe is somewhat superseded by more recent approaches, in particular measurement-based computations. And Nick might correct me on this, but my feeling at the moment is that the resource overhead associated with all these additional photons, when you don't consider fault tolerance, is comparable in the best measurement-based approaches and the best gate, conventional gate-based approaches. However, the fault tolerance thresholds for cluster state measurement-based approaches are much, much better, and there's less of a need in those measurement-based protocols. It's a local system, so you don't need arbitrarily distant interaction between photons. I don't know if Nick or Terry want to say anything further about that. Yeah. So anyway, this is sort of I guess for historical pedagogical purposes, I think this is a nice explanation, but just to bear in mind that this is not probably the way that you ultimately do things. So now I want to talk about what's going on in these linear optical networks here. And essentially what is going on is quantum interference of photons followed by measurement. And so I'll just spend a bit of time explaining quantum interference for you, which is probably a recap for a lot of people. If we have a single photon, and now by one I mean a single photon in this mode and a single photon in this mode, and they arrive at a 50-50 beam splitter. So this is 50% reflective beam splitter. So if I were to send bright light in here, half of it would come out here and half of it would be reflected. If I send two single photons in there simultaneously such that they arrive at the same time, and I ask myself what's the probability to get one photon out this output and one photon out this output, then I'd say, well, it's the probability for both photons to be reflected plus the probability, for both photons to be transmitted plus the probability for both photons to be reflected, which gives me a half times a half. But of course, that's the classical probability theory answer to this inherently quantum mechanical question. And as you know, in quantum mechanics, what we do to calculate that probability is we sum the indistinguishable probability amplitudes and take the mod square at the end. And I get a and it's this minus sign here that makes all the difference. I guess for me this is a very clear articulation of, you know, why quantum mechanics is different to classical systems, is that we have these probability amplitudes which are complex numbers and can therefore interfere in ways that their classical probability theory counterparts can't, and that's exactly what happens here. You get the same amplitude, but the opposite phase for these things will completely cancel one another. It's also this effect of quantum interference is probably the most readily observable quantum mechanical feature that you can almost get your hands on, in the sense that you can go into a lab and change the polarization or the time delay of this photon relative to that photon and see this effect come and go. You can almost sort of get your hands on quantum physics, if you like, using this feature. And what you see, for example, is if you put a delay on this photon and you measure what the probability, what the probability of getting a photon out of each of the outputs is, then you see something that goes from the classical value of a half down to 0 and back again, where this is the coherence length of the photons. And the reason that you go from the classical to the quantum regime and back again is that in writing this down, I'm implicitly saying that these two probability amplitudes are indistinguishable from one another, by which I mean there's no measurement allowed by the laws of physics that will tell me which of these two things happened, which has got nothing to do with, how good an experimentalist I am, or how good my equipment is, or how much I paid for it, or anything like that. It means that there's no conceivable measurement that would not violate the laws of physics that would allow me to tell the difference between the two. And what that means in practice is that those two photons have to be indistinguishable from one another in all degrees of freedom. So in their polarization, their arrival time, their spatial mode, their frequency and bandwidth, and so forth. It's often, for that reason, it's often incorrectly thought of as the interference of two photons, so the two photons interfering with one another. And it's quite clear from here that it's the interference of the two photon amplitudes that interfere, not the photons themselves. And so in actual fact, you can engineer a situation where these photons are completely distinguishable from one another, so they're different colors, or they never actually even are in the same place at the same time together, and you can still see this quantum interference. But unless you make a special effort to engineer such a situation, effectively you need to make these photons indistinguishable from one another. But just to be clear, that it's not the photons interfering, it's these two photon things. And I guess a few people in the audience can tell you that the original data that looked like this comes from 25 years ago, and yet people are still pretty happy when they see data like that in the lab, and often they spend many months getting to that stage. And the reason that they're pretty happy is because they spend many months, and the reason that they spend many months is making these two amplitudes indistinguishable from one another, making those photons really identical with one another. So for example, if there's a slight, if the angle's not quite right, and you end up with the transmitted and the reflected mode at a slightly different position on your detector, then you can distinguish the two of them. So any questions about that?
Why is it harder to, they only have to arrive within the coherence time.
Yep.
So you would have thought that Nicholson only photons
it's true that you need less path length stability for this than in a conventional interferometer. So what Terry's asking is, you know, if you have a Mach Ender like an interferometer like this thing, then to see interference here, these things need to be stable on a fraction of a wavelength scale, which means, you know, if you're dealing at optical frequencies, then that means hundreds or tens of nanometers, whereas here these path lengths need to be stable on the coherence length scale, which is anything from, you know, from in a typical down conversion experiment could be hundreds of microns, and for you know, atom cavity systems could be up to you know, 100 feet or something like that. So your question is why is it so hard? And the answer is that it is easier in that respect, in that, you know, you don't, if you set this thing up and you know, one of your mirrors vibrating around on the sort of hundreds of nanometers time scale, then hundreds of nanometers length scale, then you're just going to be, you know, moving around in here, and it won't cause any problem. But otherwise, I think it's the same mode matching problem outside of that. So if you think about the spatial mode matching of you know, these two beams here, I think it's exactly the same. And I guess the reason it's hard is that you've got to count single photons at the end and not look at, you know, some bright laser beam and the interference fringes of it. I was very annoyed when someone asked me whether I was going to bring the quantum laptop back, which I didn't do, but so, does that make sense?
Jeremy?
Yeah.
Sorry, could you explain what you mean by coherence length? That doesn't mean the size of the wave packet? Or
Yeah, so it just means the temporal or you know, the length of the wave packet of the photon. Yeah. And that can vary dramatically, as I sort of alluded to, from, you know, it can be on any scale in principle. But in contrast with a conventional interferometer like this, or a microscope interferometer, which is the same kind of thing here, then these path lengths need to be stable to a fraction of a wavelength for you to see interference.
Jeremy, in a typical waveguide, what kind of bandwidth can you allow to remain transmitting good? Well, because obviously a greater bandwidth will give you a much narrower wave packet, which will make the photons harder to distinguish between.
Yeah, you're absolutely right. So the you know, this, you know, if you measure this in time, or, you know, coherence time or coherence length, then the shorter that is, the more challenging it is to see this effect. The good news is that, you know, in a waveguide architecture, those path lengths are, you know, very precise and very stable, and exactly what that bandwidth is determined by the source, nominally, of photons that you use. So in a standard down conversion source, the bandwidth might be, you know, a few nanometers to a fraction of a nanometer, which means, you know, hundreds of microns. And if you take a, you know, rubidium atom in a -S optical cavity, then you end up with photons that have a coherence length of 100 feet or something like that. In fact, we've done experiments in collaboration with Axel Kuhn at Oxford, sending those photons that are hundreds of feet long through the same devices. Any other questions about that? I have a question. Where do they go then if there's no probability for the photons to come out here and here? Where do the photons end up? Sorry?
Two up or two down?
Two up or two down, yeah. That's very good. It's an interesting thing. Obviously, you know, you start by thinking about the classical, you know, there's four things that can happen, right? and they are the four things. And then you work out, well, these cancel with one another, so there's no probability for this to happen. And so you get an enhancement of the probability for these things to happen, and in fact you're in a coherent superposition of both these things. To see that actually more directly, we can do a more complete analysis of this situation here. If I now just make this an arbitrary reflectivity eta, then I talk about the creation operators for the input and output modes here. And you're all happy with these operators which, for example, act on the vacuum in mode A to produce one photon in that mode. You can define annihilation operators and operators and so forth. Here it's fairly straightforward to convince yourself that we can talk about in quantum mechanics, we can talk about states and how they evolve. We can talk about operators and how they evolve, and it turns out with linear optics you're many times better off, although mathematically they're completely equivalent to one another, you're much better off looking at operators, and you just have to do a few examples of where you use states and how they evolve, and find that it's very it's much more difficult. Anyway, I can write these output operators in terms of the input operators. Like this. So I'm just expressing what we already know, which is that in probability amplitude as opposed to probability, I get a square root of eta of this mode reflected, and I get a square root of 1 minus eta of this mode transmitted in this output, and so forth. Is that clear? And the time reversal symmetry of this situation allows me to say, right, this is exactly the same expression for the input operators expressed in terms of the output operators. And what I'm interested in my original problem was when I send a single photon in here and a single photon in here, which is this state. So if we calculate this operator, we can see what comes out at the output, and that's just a simple bit of algebra, which even in my hungover state today I might be able to work out. Now these operators commute. They creation operators in different modes commute, so I can group these terms together. So I get an eta plus 1 minus eta. I said I was going to be able to do it, but I'm not seeing it is. So I'm going to group these two things together. So I get an eta plus a 1 minus eta. And then I've got these. And then I should operate this operator on the in this mode, but you can clearly see what this does. It creates 1 terms here, and it creates 2 0 minus 0 2 terms here.
You missed the minus sign.
Whereabouts?
In that first bracket, then eta plus 1 minus eta. If I
One
use minus.
should have.
Yeah,
Thank you.
doesn't work out well.
I thought I was going to be able to do it, but it turned out not. Yeah, so that, you know, you see this is the term that we just convinced ourselves by a simple argument was 0, and now you see that if you set it equal to a half, then you've got minus half plus 1 minus half, which is 0, so you've got no 1, 1 component in the state, and you're completely in this coherent superposition of 2, 0 minus 0, 2. So far, so good. Okay, so that's just a more complete picture of what's going on here in quantum interference, and you see that if eta is not equal to a half, then this 1, 1 term is not completely cancelled, but you see that the probability amplitudes for these two events always tend to cancel one another and are always less than what you get in the, you know, for the probability of a classical situation. So, you know, this is always lower than what you get for the classical analysis. All right. So, that's it. That's really the whole story with you know, linear optical quantum computing and photonic quantum technologies and anything you might want to do with photons. Pretty much that's it, right there. That's all you really need to know, and that's what makes it distinct from any other system. What I'd like to do now is explain to you how a CNOT gate works, relying on this effect. And I guess what I'm going to start by doing is talking about this controlled high phase shift that sits at the heart of this thing here. So you can convince yourself that this controlled pi phase shift, or so sandwiched with two Hadamard gates, is what I've got here. So I've got this beam splitter that implements this here, this Hadamard operation here and here, and then the interesting and hard part is realizing the controlled pi phase shift here. And as I had the logic table drawn up before for a CNOT gate for a controlled phase shift. It just puts a minus sign on this term. The reason that I'm doing this is that I'm going to show you how this part works. But is that clear enough? Only one person has to say it's clear, and then it's clear. So what I'm going to do now is I'm going to draw up a circuit that does this operation and does it with probability not equal to 1. And I'm just going to draw it up, and then I'm going to step you through and convince you that it really does what I claim it does. And the circuit is quite simple. You've got your control and target again encoded in path like this. And I have a sequence of now 1/3 reflectivity, 2/3 transmissivity beam splitters. Like this. And this does this controlled Z or controlled pi phase shift operation here. And so what I'm going to do now is just consider those 4 computational basis inputs here and show that I get the right output with non-unit probability, and I'm not going to worry about the rest of the time when it fails. It works when I get 1 photon out the control output and 1 photon out of the target output. So if I get a photon out of each of these outputs, then the gate just works. I'm not going to worry about the rest of the time, but I'll keep track of the probability amplitudes. And I'm going to get a phase shift on reflection off of this side of these beam splitters and this side of this beam splitter. So that's the same phase shift that gave us this back here, there's a minus sign. Space should be here. And I'm in this analysis, I'm pretty well free to choose which side that's on. I should have maybe emphasised at the time that physically, if I get a beam splitter from Thor Labs, it's got an alpha phase shift on one side and pi minus alpha on the other side, and there needs to be a net pi phase shift difference between reflection off of each side of the beam splitter. In a waveguide device, because you hope that everything is very symmetric, and it is, you end up with an I phase shift off of both sides of things. But in terms of analysing these circuits, you're pretty well free to choose whatever convention you want. And I'm going for this asymmetric, high phase shift on one side and nothing on the other. And some people formulate things where they have a symmetric beam splitter with an I phase shift on both sides. It doesn't really make any difference. Is that okay? Okay, so I just look at these states. So if I put the 0, 0 state in, what happens? Well, that's one photon here, one photon here. There's only one way that this gate can work, and that is if this photon gets reflected here, and that happens with an amplitude of 1 on root 3, and this photon gets reflected here with an amplitude of 1 on root 3, and then the photon has come out in the same state that they started with. And similarly, if I have the 0 and 1 state, it's a photon here and a photon here, and it's exactly the same sort of argument. This is more interesting if I have the 1, 0 state, that's a single photon here, and a single photon here, and there's two ways that I can get a photon at the target, at the control and target output, and that is if they're both transmitted or both reflected, and that's exactly what I just calculated here. It's this term that we're interested in, when they come out in different outputs. And for eta equal to a third, I've got minus a third plus 1 minus a third. And then finally for the 1, 1 state, it's the same as these two. This has to be reflected. This has to be reflected, but you see you get a minus sign. So with this simple circuit, if I send in a single photon in the control, a single photon in the target, with probability 1 in 9, I get a single photon out here and a single photon out here, and I've implemented this controlled pi phase shift or CZ, controlled Z gate on them. It's minus a third, right? And you see basically what quantum interference is doing for us here is two things. It's making this amplitude the same as the others, and it's making it positive where it might otherwise be negative. If that was negative, then that's a completely unentangling gate with very little use. You can simply put a minus sign there, then that's not an entangling gate of any value to us. And can you suggest why it might be important for the amplitudes to be the same in magnitude?
Otherwise, you don't have maximum entanglement.
I think you could still generate a maximally entangled state for a given input.
But not.
Or given input, not superposition. Isn't that the problem?
Yeah, I think you could still generate a maximum entangled state, but yeah, there's another good reason why these amplitudes should all have the same magnitude.
You have a constant probability of showing up CZ gates and not something else. Because CZ has to have just 1, 1, 1, minus 1, and then
Yes.
just one of it will come out.
Yes, yes. So you've got a CZ gate with some probability.
Mm.
Yeah, yeah. That's exactly right. I mean, the way I describe it is that, you know, imagine that these are vastly unequal. These amplitudes, so that, you know, one of them was near unity and all the rest of them were near zero. Then knowing that the gate had worked would tell you with near certainty what the input state was, right? And so you haven't gone all the way to measuring the input state, but you've gone a long way to doing it. So you've done a partial collapse of the wave function. You've massively perturbed the information. So any deviation from equal probability will tell you something about the input state of the gate. The fact that it works, you'll know that it's more likely to have been the input state that has the highest success probability coming out, and obviously that's going to... Okay, so that's it. Is that any more questions about that gate?
So would it only work 1/3 of the time, the other time you get 2 photons in one application?
Yeah, 1/9 of the time it works in that I get a photon out here and a photon out here, and the rest of the time, for example, a photon comes out here, or I end up with 2 photons here or 2 photons there. Yeah. And then what I do with something like this is apply what I showed you in the previous time. I apply this sort of teleportation trick. Any other questions?
Jeremy, is it a problem that it only works 1/9 of the time? On a computer, it doesn't need to happen to this time.
Yeah, well, 1/9 to the power of n is a pretty small number for any n. So by itself, it's a problem. The solution, at least in the original KLM recipe, is to do this teleportation trick. In the measurement-based or cluster state type approach, the idea is that you try to generate this this cluster state, so this large entangled state where, I mean, in the simple picture of this, you start by preparing each of these physical qubits in the plus state, and then you run the CZ gate, the same sort of gate, everywhere that you've got bond. And in this case, it's I don't know whether you'd say it's less problematic, but in essence, you can do some sort of random walk to build up that cluster state. And I guess Mike Nielsen's insight was that when these KLM gates fail, they make a Z measurement on the qubit, and that's precisely the type of thing that cluster states are robust to. So if you make a Z measurement on one of these qubits, you can simply remove it from the cluster, but the rest of the state is intact. So you go along and basically try and build up the cluster bit by bit. Sometimes you succeed in adding a qubit, and sometimes you knock one off, and as long as you're on average growing it, it's fine. So to reiterate, in the original KLM recipe, you take these non-deterministic gates and you use this teleportation trick owing to Gottesman and Schwung, which allows you, by using additional photons, additional entangled photons and single photons, to make that arbitrarily close to unit success probability, and then just use that as your fundamental building block. And in cluster state approaches, you use a gate like this, or Terry's fusion gate, to build up ever larger clusters in a non-deterministic way.
How do you know when to use the trick? Like, how do you know it doesn't work? When it doesn't work?
So, this is a heralded gate. So coming back to this picture, and I'm hoping someone will ask me the question in a minute. I know that this gate has worked or it hasn't worked based on if I detect a single photon here and a single photon here, it's worked.
This is okay, but do the double bottom there?
Here?
Yeah.
So here, I know it's worked when I detect a single photon here and a single photon here.
Okay.
You've destroyed the state.
And I've destroyed the state.
Okay, you can destroy it.
So you can concatenate that here.
That's right.
As another
That's right. That's right. So you see that this doesn't have those two auxiliary it doesn't have these two auxiliary photons here and here, and it works. I know that it's worked when I measure these things, which is not very good for concatenating it into a large system. In principle, I can make a measurement of there being a photon here without destroying that photon. You can do a quantum non-demolition measurement of that photon, and in fact, it turns out that you can do that using some auxiliary photon, single photon detection, and some linear optical network. And then you see that you've got two of these things. And now you see that actually looks very similar to here. Turns out that for the best known procedures for this element and these elements, you end up with a success probability that's 1 in several hundred or maybe even 1,000, I'm not exactly sure. But anyway, much lower than the success probability of this gate here, where you sort of directly incorporate those auxiliary photons into the system. So in practice, you'd never go ahead and do things like this, but at least conceptually, you can pull apart the two elements.
Jeremy, does heralding work if your detectors, well, okay, obviously that's a yes, otherwise you would be out of a job, but if your detectors aren't perfect, what happens to heralding? What's the problem there? I mean, there should be a problem, right? Or...
Yeah, so there's several things here. The detectors have a finite efficiency, and they may or may not resolve the number of photons coming out. And it turns out that you don't need number resolving detectors, but they will help you if you have them, so that you gain a reduced sort of complexity to the system if you have number resolving detectors. And in terms of the efficiency, that all goes into fault tolerance, which I actually have no idea what we'll talk about. I was going to ask you in the final session, but maybe that's a topic to cover a bit. But I guess quantum computing is a waste of time without fault tolerance theory, right? Which tells you that, well, we know that things are not going to work perfectly. We have, these fragile quantum systems, and it tells you that if everything works above some threshold, then you can do an error encoding scheme, concatenate, several layers of physical qubits to logical qubits, and that you can do an arbitrarily size and length computation. And so the efficiency of detectors is just one of those error things, and as long as they're above some threshold. And I guess the really positive news for photonic approaches to quantum computing is a result by Terry and Dan, Brent, which shows that if everything works perfectly except your single photon sources and detectors have non-unit efficiency, then the product of their efficiencies need only be greater than a half for you to do an arbitrary scale computation.
Which is probably satisfied already by what you can buy, right?
Yeah, and then then lost throughout the circuit, you can imagine as being part of the source or detector efficiency and so on. So basically, in summary, you can lose half your photons and you can still do an arbitrary scale computation. Of course, everything else doesn't work perfectly, and an open question that we're working on between us in Bristol and Terry and colleagues at Imperial is whether you can turn all errors into loss. And I think it remains an open question, but there's some reason to think that you can. So, for example, if you have a single photon source, you press the button and it comes out with some temporal jitter, for example, so it's not in a perfectly Fourier transform limited pulse, then you can spectrally or temporally filter that, which means that after the filter, if the photon gets through. It is in a in a perfect pure state, in a perfectly time bandwidth limited pulse, and that's turned that into loss. So with some probability it gets through, and some probability it doesn't. And if it gets through, it's in this nice state. So you've turned what is a sort of typical decoherence type looking error into a loss error. And if you can do that, then you can be in this regime. I guess the summary is that things will go wrong with your quantum computer, however you build it. But the best possible thing that can go wrong is for you to lose your qubits. The threshold for losing qubits is much, much better than anything else that we know of. And of course, that's the principal error that will happen with photonics. And the difference from all other systems is this sort of zero temperature environment where there is no thermal bath that photon is coupled to, in contrast to any other physical system that we know of. So I promised to finish at 20 past, which is now. Some questions and maybe some suggestions for what to do in the final thing. I can put some slides together. I guess I was thinking to give you kind of more of a research talk for the last thing and maybe just update you if that's the sort of thing. But I'm conscious that I've talked exclusively about optical quantum computing, but as I said at the start, the analysis and the physics is the same whatever you're doing, whether it's quantum metrology or communications, exploring the foundations of quantum mechanics with photons, it's all the same sort of thing. So maybe I'll give you a flavor of that thing. But if anyone wants to tell me what they'd like to hear in the thing, and I might actually get Nick to give us the final talk as well.
Talk on non-universal models of computation. Do you use pause sources?
Yeah, so maybe I'll get into a bit of technical detail in the last thing. Well, maybe I'd like you to tell me what you want to hear in the final thing. But for example, I can tell you, how we generate and detect photons, and how we realise these circuits and so on. Maybe that's the.
I want to see what you've actually been doing.
Yeah. Okay.
And just how it works.
Okay. All right. That's a clear steer then.
Yeah. Feel free to contribute.
I want to see what you're actually doing. Good. Tell me over lunch as well if you have any things that you'd like to hear about. And I guess we have a few minutes for questions and we'll go to lunch.
Any questions?
Is there any hope of building like an actual non-demolition detector rather than one of these fake ones? Presumably, is there like a principled reason why you expect the other to be able to do that?
Did you say is there an in-principle reason?
Yeah. Well.
No, you can do it. We've done a measurement, a quantum non-demolition measurement, which is, at least in the picture of single qubits, is just a fancy name for a projective measurement as far as I'm concerned, in the sense that it's the textbook projective measurement in that you get the outcomes with, according to the probability amplitudes, and then afterwards you're left in the state that you measured the system to be in. And we've done that for the polarization of a single photon, and it's doable. I don't think people have certainly done QND measurements of photon number. Here it's a bit tricky because what you want to do is you want to measure. This is what you're talking about, right? You want to measure whether this photon is across these two modes. So, for example, it means measuring whether there's a photon there without learning what its polarization is. But that's absolutely doable using these same linear optical techniques. In practice, you would never do it for the reasons that I described, which is that if you pull things apart like this, then the success probability of everything is much, much lower than direct. I mean, in some sense, that's what this is teasing apart this picture over here, right? In the, you've got this sort of effective nonlinear interaction between the two photons, and then part of that operation is to see that they come out in the right place. And that does it all sort of, in a concatenated fashion.
Yeah, I mean, I got that if you did it using these linear networks, then it's worse than just doing this thing that's kind of joined together. But what I was wondering is if there's like a way of actually building, I don't know what you call it, like one that doesn't require an ancillary plate selections.
Yeah, I mean, it's
then this would actually be quite a good thing, right? 'Cause
yes, yeah.
doesn't-
So you know, if you have a real physical non-linearity that you can implement between photons, basically, whether it's a C0 gate, a Bell state measurement, or a QND measurement, you effectively need some sort of interaction between photons to do that. And outside of this linear optical picture that I've articulated here, you'd need some sort of atom-like system in an optical cavity, for example, to do that, and there are schemes to do exactly that. And in fact, if you had something that could do any one of those things, it would be relatively straightforward to adapt it to do with the other two things as well. So and in fact, you have a pretty good single photon source as well. So if you had an atom cavity system, then you should be able to, you know, hit a button and spit a photon out. You should be able to use that to mediate an interaction between pairs of photons. You should be able to use it to do these Q&D measurements, for example.
But in practice, the cavity schemes within QND, you know, they're sort of, well, the Roche has done some of them. They're not completely infeasible if you want to do QND measurement between 0 and 1. But in this, you would have to do it between 0, 1, and 2. And, you know, each time you want to be able to do a QND measurement of a higher and higher clock state, it just gets harder to sort of separate out the signal. So I think even if we had QND measurements, we wouldn't use this circuit because it has this failure mode of, you still need to get out the two photons. You can come up with similar circuits that don't.
Yeah, I mean, maybe just to take a step back, what I've tried to give you a picture of here is the all linear optical approach, where you don't have any sort of atom cavity system or any exotic nonlinearity of any kind. But once you have that, you almost throw all of this out and you can do all of these things. And I guess in the next hour, I'll try and explain to you why that's very appealing to not have such a system from a practical perspective.
There are no more questions, as thank you very much.